Hey guys, so this video is on precision and accuracy. So let's first define what those two terms mean. Accuracy tells us, or what it is a measure of how close a measurement, or if there's more than one measurement, the average of those measurements is to the true value. The way that we calculate accuracy is percent error. And this right here is the formula for percent error. And it's a pretty easy formula. All you do is you take the experimental value, or if it's a series of measurements, the average of that series of measurements, minus the true value of the true value times 100%. If you get a negative number here, that just means that your measurement or average is lower, that percent lower than the true value. If it's positive, that means it's higher. Precision, okay, on the other hand, is a measure of how close a series of measurements are to each other. So the way we measure precision is with something called standard deviation. And we use the sample standard deviation. And this is the formula. So sigma stands for standard deviation, and it's equal to the square root of the sum of each of the individual measurements, that's our x sub I, minus the average. Mu stands for the average. Okay, the difference between the one measurement and the average squared, plus the sum means add them up, plus the second value minus the average, that squared, plus the third minus average squared, and so on, all divided by the number of measurements minus 1. So what standard deviation can give you is a feel for if there is a random error introduced into the experiment. What it will not do is give you a feel for whether or not there is what we call a systematic error introduced into the experiment. So for example, let's say you're measuring the mass of something, say 10 mils of water, and it ends up that the balance that you're using is calibrated wrong. So it's, let's say, 1 gram off all the time. Any measurement you make is 1 gram off. So you could get like a series of measurements of that 10 mil, the mass of that 10 mils of water that are very close to each other, but they'd all be about 1 gram off. So that would be that would be a systematic error, that balance not being calibrated properly, and you would get a small standard deviation, but you would get a large or a bigger percent error because the average of those measurements, even though they're close to each other, would be about 1 gram or so off from the true value. So that would give you a percent error. So percent error, one of the things it can do is show you if there is any systematic error showing up. What the standard deviation can do is tell you if there is any random error showing up. So a random error would be something like you don't measure the 10 mils of water carefully, and so you have actually a different amount each time. So your measurements would be different from each other, and so the standard deviation would be larger. All right, so let's apply these. So let's say we have a series of measurements, and what we're doing is we're measuring how much 5 milliliters of water weighs, 5.000 mils. These numbers in white, let's say these are the 5 masses we got. We measured 5 mils of water out 5 different times, and we got these masses. And it ends up that at the temperature of the experiment, the true value for the mass of 5 mils of water is this many grams. It depends upon what the temperature is it ends up. You'll see that later. So 4.9986 would be the true value. Let's say we do another experiment where we measure the same thing, the mass of 5 mils of water, and we get these numbers. Maybe we're using a different balance, or somebody different is doing it, or we're just doing it at a different time. What we want to know is find out which of these sets of measurements is more accurate. That means we want to know which has the smallest percent error, and which is more precise. That means we want to know which has the smallest standard deviation. So let's go do that. So for both of those calculations, we're going to need to know what the average or the mean is. And so we just add up and divide by the number of measurements. So for set 1, we add them up, divide by 5, and we get this number right here. For set 2, so now let's calculate the percent error. So the average value minus the true value of the true value times 100. When we do the subtraction, we keep 4 places past the decimal, which gives us 4 significant figures in our answer. and we get negative 2.829 rounded percent. All right, now let's look at the second set. There's the average, 4.8818 grams, calculating the percent error. The average value minus a true value, same true value, times 100%. We get a negative 0.1168. Negative, remember, tells us that our average is lower than the true value. Keep 4 past the decimal, so we end up with 4 significant figures, a negative 2.337 rounded percent. This is smaller than the percent error for the first set, which was negative 2.829%, so we can say that the second set of measurements was the more accurate of the two. So now let's find out which is more precise. So we're going to calculate the standard deviation, and I've plugged into the formula for standard deviation for set 1 and set 2. And you should do this, make sure you get the same number I do, and see how that formula works out to be what I wrote up here. This number here, the 4, is the n minus 1. So n was 5 because there were 5 measurements, n minus 1 is 4. That's an exact 4, by the way. So I end up getting the standard deviation for the first set of measurements as 0.219 grams. Notice, by the way, the standard deviation has the same units as the measured values. Percent error, it has no units, it's just a percent. The standard deviation for the second set was 0.146 grams. So the standard deviation for the second set is smaller than the standard deviation for the first set of measurements. So we can say that that set 2 has a smaller standard deviation. That means it's more precise. Now in this case, with these sets of measurements, we ended up with the more precise measurement being the more accurate also. That's not always the case. Sometimes one set is more accurate and the other is more precise. So last thing is the way we would report the results of this experiment is we'd say for set 1, the average mass is 4.8 grams plus or minus 0.2. The plus or minus 0.2 is because the standard deviation was 0.219. We just take the first non-zero digit. And whatever place that's in, that's the last place we can report with any confidence in our average measurement. So it doesn't make sense to say anything past this 8 because if there's an error in that 8, we know it's plus or minus 0.2. It could be 5 grams, it could be 4.6 grams. The second set, because the standard deviation was 1.149, the first non-zero digit is 0.1, so we'd say the average 4.8 plus or minus 0.1 grams.